In this video, we're going to discuss errors in the midpoint, trapezoidal, and Simpson's rules. So we've already talked about how to apply these rules to approximate an integral, but it would be nice to know how good those approximations are potentially. So, to that end, let's discuss how we can use some formulas associated with these rules to give us an estimate about how good our error is, and also how to use this formula to help us make sure that we get our integral within a certain tolerance level. So we'll see some examples of both of these. So we're going to use the letters e sub m, e sub t, and e sub s to represent the errors when we approximate the integral from a to b of f of x dx using each of the three rules. Okay, so by error, of course, we mean if we take the value that we computed and subtract off the value of the actual integral, that gives us the error. Okay, we would like to know how we would like these errors to be small, of course, because we want the approximation that we do to be close to the actual value. All right, so this is going to look a little bit weird, but we're going to talk about why these we might be interested in these particular quantities. Let's suppose that the absolute value of the second derivative of the function is less than or equal to some constant over the interval that we're integrating. And then let's suppose that the fourth derivative is also less than or equal to some constant over the interval that we're integrating. All right, so let's talk about why we might be interested in these particular quantities without going into too much detail. Remember that when we did the midpoint and the trapezoidal rule, we're trying to approximate the function using line segments. Right? The midpoint rule, we used the horizontal segment that was the top of a rectangle. The trapezoidal rule, we used the segment that was between the two endpoints of the subintervals that we're looking at. But in any event, for both of those rules, we're using a straight line segment in order to approximate the function. Straight line segments have no curvature where the function might. So if we look at the errors in the midpoint and the trapezoidal rule, it makes sense that the error would depend on the second derivative, because the second derivative is a measure of concavity or a measure of how much the function is bent. Now, also remember in Simpson's rule, instead of using segments, we used parabolas to approximate the function. Certainly, parabolas have some bend to them, right? But past the second derivative, the parabola has no other information to give, right? So when we take the second derivative of a parabola, we get a constant. So there's not any other information to get past the second derivative, because once you get to the third derivative of a parabola, you would get 0. So it makes sense for Simpson's rule that the error would not depend on the second derivative, but it might depend on the fourth derivative, because again, the function that we're trying to approximate might bend more, or at least in a different way than what the parabola does. So in any event, even if you don't want to think about those ideas, just remember that the midpoint and the trapezoidal rule depend on the second derivative for the errors, whereas the Simpson's rule depends on the fourth derivative for the error. All right, so here are some error bounds. If we want to look at the absolute value of the error in the midpoint rule, then notice again it's in terms of that constant for that bounds the second derivative, k times the length of the interval cubed, so b minus a cubed, divided by 24n squared, where again n is the number of subintervals we're talking about. For the trapezoidal rule, it looks very, very similar, but instead of a 24 on bottom, we have a 12. All right. For Simpson's rule, now again, we won't use the k because the Simpson's rule uses parabolas, which takes into account some of the bend in the function. So we're going to use the L, that's the bound on the fourth derivative, times again the length of the interval, b minus a to the fifth power, and then divide by the 180 times n to the fourth. So these are the error formulas for midpoint, trapezoidal, and Simpson's rule that we're going to use to either get an idea of how good our approximation of the integral is, or to see how many subintervals we will need to get to within a certain tolerance level that we want. All right, so let's look at this integral. We want to estimate the error in approximating the integral from 0 to 2 of 1 plus x cubed all raised to the 5/2 power dx using trapezoidal rule and 10 subintervals. Okay, so the most complicated part of doing this is actually finding the upper limit of what the absolute value of the second derivative can be. Okay, that can get complicated. So the ones that you'll have to do will be relatively rigged so that you can actually do it. First, we'll compute the second derivative. All right, so here's our function. First derivative, we have to use chain rule. We bring the 5/2 down, decrease it by 1. That's where the 3/2 power comes from. Derivative of the inside is 3x squared, so when you do the 3 times the 5/2, that's where the 15/2 comes from. To do the second derivative, we have to use a product rule. Derivative of the first will give you your 15x. Derivative of the second, you're going to have to use a chain rule again. The 3/2 will come down in front and decrease the power by 1 to get to 1/2. And then derivative of the inside is your 3x squared. If you do all that work and multiply by the 15x squared over 2 out in front, you'll get 135x to the 4th over 4. Okay, that's the second derivative, right? We need to maximize the second derivative, but not just the second derivative. We need to maximize the absolute value of the second derivative. That can get complicated. Now, for a very, very, very complicated function, what I would suggest doing is graphing the function in your calculator and figuring out the absolute top it can get in the positive direction, the absolute bottom it can get in the negative direction, and then pick the number that has the biggest absolute value. You're probably not going to have anything that complicated. We should be able to reason through this. All right, so the first thing we notice is on the interval from 0 to 2, the second derivative here is positive. There are no negative signs anywhere, right? So maximizing the absolute value is the same as maximizing the function. Also notice that if we were to take the third derivative, that's how you maximize a function, right? You take its derivative and analyze its derivative, right? If we were to take the third derivative, no negative signs are going to pop up, right? Everything here has a positive sign. The only place where you could possibly get a negative would be if you had a negative exponent and bringing it down in front. We don't have that yet, right? So we notice that it's always going to be positive. The function's always positive. The second derivative is always positive. And the third derivative will also always be positive, no matter what. Well, that means the second derivative is actually increasing on the interval from 0 to 2, right? Remember, positive derivative means function is going up. So if the function is always increasing, its maximum value must occur at the right endpoint, which in this case is x equal to 2. So the maximum value of the absolute value of the second derivative, which is the same as the maximum value of the second derivative, has to be what we get when we plug in 2 into the second derivative, which in this case we get 2,430. Now we're ready to compute the error. We've got the maximum value, that's the k. We do the length of the interval, 2 minus 0 to the third power, and then divide it by 12 times the number of subintervals squared, and we were told that we're using 10 subintervals in this case. Then if you simplify that, you get 81 over 5, or 16.2 if you prefer the decimal. So if you're integrating this function, or trying to compute this definite integral, I should say, using trapezoidal rule, to get that approximation using the trapezoidal rule, then your answer that you get should be within a little over 16 of the actual answer. Whether or not you think that's good enough depends on the application that you're doing. Let's do another one. Let's say we want to estimate the error in approximating the integral from 1 to 3 of log x dx using Simpson's rule and 6 subintervals. All right, so remember with Simpson's rule, we have to get a bound on the absolute value of the fourth derivative. Well, let's do the fourth derivative then of the function. The function is natural log. Its derivative is 1 over x. Makes the second derivative 1 over x squared. Third derivative will be negative 2 over x cubed. Fourth derivative will give us 6 over x to the fourth. Again, if you're trying to maximize this function or maximize the absolute value, typically we would look at the fifth derivative then and analyze the derivative. But again, notice that this function is positive on the interval from 1 to 3. And as x gets bigger, the fraction gets smaller. So this thing's always decreasing. You could also see that from doing the fifth derivative. The fifth derivative will be negative, but in particular, this function is positive and decreasing the entire time. Well, if it's decreasing, that means your maximum value occurs at the left endpoint, which in this case is 1. So we can find the maximum value simply by putting 1 into the function and getting out 6. Now again, we're ready to calculate the error. The error in Simpson's rule again is bounded by the maximum value of your absolute value of your fourth derivative. So in that case, that's the 6. That's the L value back in the formula, times the length of the interval, 3 minus 1 to the fifth power, and then divided by 180 times the number of sub-intervals, which is 6 in this case, raised to the fourth power. In this case, you get 8 10,000ths approximately. So notice that this is a really, really good approximation using a few number of subintervals, right? We only had to use, it says we're only using 6 subintervals, and we're getting a darn good approximation. So this is one of the reasons why we like Simpson's rules over the other ones, is because the error gets better faster. Okay? All right, so let's do one more. Instead of looking at given the number of subintervals and calculating the error, let's say we want to have a specific error goal to meet, and we want to know how many subintervals we need to guarantee that tolerance. So let's suppose you're given values for the second and fourth derivative, bounds I should say on the second and fourth derivative, over an interval, and we want to know how many subintervals do we need to approximate the integral from negative 2 to 1 of f of x dx to within 1,000th using the midpoint rule and using Simpson's rule. First, we need to, for the midpoint rule, we need to figure out that value of k, the bound on the absolute value of the second derivative. Okay? So if the second derivative is between negative 4 and 3, the absolute value could get as big as 4 because of that 4 there in the negative direction. So 4 is what we're going to use for the k value. Now we just have an equation to solve. Or actually, I'm sorry, we have an inequality to solve. We want the error to be less than or equal to 0.001. Well, if we use the bound on the error and make sure it's less than 0.001, then the error will be less than 0.001. 4 is our k value. 3 is the length of our interval. Cube that, divided by 24n squared. Rearrange your inequality here. You'll get n squared is greater than or equal to 4 times 3 cubed over 24 times 0.001 in your denominator. Means your n squared has to be at least 4,500, or your n has to be 67.082. Now, remember, n is representing number of subintervals. Number of subintervals has to be a whole number. We want to guarantee that we are within this tolerance range. If we round down, we may not have enough subintervals. So we always, no matter what the decimal is, we always round up, period. So we have to have at least 68 subintervals here. And again, that's because you have to have a whole number of subintervals, and 67 might be too few, right? Because this says n has to be at least 67 and change, not 67. So we always round up. All right, for Simpson's rule, if we look at the absolute value of those two numbers, 35 is the bigger of the two, so we know that the absolute value of the fourth derivative is less than or equal to 35. Now we use our error bound formula for Simpson's rule. If we want the error for Simpson's rule to be less than 0.001, then we want that error bound to be less than 0.001. 35 is that L value. Here's the length of the interval again, raised to the fifth power, divided by 180 n to the fourth. Rearrange, you'll get 35 times 3 to the fifth over 180 times 0.001, which means the fourth power of n has to be at least 47,250, which means your n has to be at least 14.743. All right. So just like we talked about last time, the n has to be a whole number. However, in this case, we also have the added condition that we're using Simpson's rule. Simpson's rule requires an even number of subintervals. So just like before, we always round up, but for Simpson's rule, we always have to round up to the next even, because you have to have an even number of subintervals to use Simpson's rule. So in this case, we have to have at least 16 subintervals. We round up because we have to be greater than 14. We can't stop at 15 because 15 is odd. We have to go up to 16.